Hello everyone, today our group will be presenting on electrochemical impedance spectroscopy, also known as EIS. EIS is a very powerful technique used in electrochemical, material science, and battery research. Here help us understand how the system responds to a AC signal and how different processes inside the system behave at different frequency. Throughout this presentation, we will explain what EIL is, the theory behind it, and how it is used in real application. Next, please. Our group members are me, Toaga, Alternatry, Gongkanli, and Yame, Ken, and Miss Susani. And so we have all contributed to preparing this content and explaining the important concept behind EIS. What is electrochemical impedance spectroscopy? To understand EIS, let's break down the name. Electrochemical means the relationship between electrical signals and chemical reactions. Impedance means how much a circuit resists the flow of AC current. Unlike similar resistance, impedance also include effect from capacitance and inductance. And spectroscopy means observing a response over a range of frequency. So in simplest terms, EI is a technique that applies a small AC signal to a system and measure how it responds to respond at different frequency. This helps us study the internal process of battery, sensor, corrosion system, and many other electrochemical devices. Next, please. Uh, Basic background theory. To understand impedance, we start with a very basic theory, Ohm's law. Ohm's law tells us the resistance are equal the voltage V divided by the current I. This works perfectly in a simple DC circuit where the voltage is constant and the current is constant. However, in AC system, things become more complicated. The currents and voltage constantly changes with times, usually in a sinusoidal wave. Because of that, we can't just use similar resistance. We need a new constant called impedance, which includes both the magnitudes of resistance and the effect of phase shifts between voltage and currents. In EIS, both voltage and currents are written as functions of frequency because the response of a system changes depending on how fast the signal oscillates. Next, please. Uh, Ohm's law works nicely in DC, but in AC systems, so it's not static. The voltage keeps changing directions and amplitudes because of this. Components like capacitors and inductors behave differently depending on the frequency. So instead of using R, we use Z, which is impedance. The impedance equation is Z equal V of omega divided by I of omega. So here omega represents the angular frequency. As frequency increases, the behavior of electrochemical system also changes. This is why studying impedance across many frequencies gives us deep information about the processes happening inside the materials or device. In summary, the shift from DC to AC analysis is the reason EIS can provide so much more detail than simple electrical measurements like DC resistance.
Okay, uh, on this slide, we compare two main modes of electrochemical impedance spectroscopy, potential studies and governor study EIS. In potential study EIS, we apply a potential signal to the system and measure the resulting current. In contrast, in governor study EIS, we apply the current signals and measure the resulting potential. The diagram shows that the input signal, either voltage or current, passes through the electrochemical system and produce an output signal with efficiency. This output helps us understand how the system responds to AC. Uh, Next slide. Here we focus more on potential static EIS. In this method, the input potential is described by the equation A or T equal to E0 cos omega t. What E0 is the amplitude, omega is the angular frequency, and omega t represent the phase of the waveform. The system responds by generating a current output I naught t, where I I0 cos omega t minus theta, where theta is the phase shift. The key point is the output current depends on the impedance or electrochemical system. By analyzing both the magnitudes and phase shift of the current, we can extract important information about the system behavior at the different frequency.
I will present about magnitude impedance. On this slide, we define the magnitude impedance. Impedance tells us how strongly a system resists AC current. The equation is very straightforward. Magnitude thus is the voltage amplitude divided by the current amplitude. And if you look at the figure below the formula, you can see a bar plot. And the red dotted curve shows the magnitude of the impedance versus frequency, and the blue curve shows the phase angle. The x-axis is frequency on a logarithmic scale, and one thing we notice in a figure is that impedance usually changes with frequency, and sometimes it drops sharply and then rises again. The phase angle also shifts from positive to negative depending on whether the system behaves more like a capacitor or a resistor. This plot helps us understand how the system reacts at low, mid, and high frequency. Next, please. And in this slide, we look at impedance in polar form. And instead of plotting impedance over frequency, we showed it as a vector. And in figure 5, on the left, the magnitude Z is drawn as a ray coming from the origin, and the angle of the ray is the phase angle theta. And this gives us a clear picture of how much the signal leads or lag. In figure C on the right, the same vector is broken into two components, the horizontal real part, which is cos theta, and the vertical imaginary part, which is the sin theta. This breakdown is important because electrochemical systems often have both resistive and capacitive behaviors. The real part tells us the pure resistance, and imaginary part show reactance from capacitor or inductors. Polar coordinate make this relationship more intuitive. Okay, next please. Okay, in this slide, we can see the Nyquist plot, which is one of the most important way to visualize EIS data. And in this figure, the x-axis represent the real part of impedance, and y-axis represent the negative imaginary part. Unlike both plots, the Nyquist plot does not show frequency on the axis. Instead, each point corresponds to a different frequency. The curve shape in the plot usually form semicircle. The left and the sub give the solution resistance, and the width of the semicircle show the charge transfer resistance. Larger semicircle mean higher resistance to electron transfer. This plot is very useful because it allows us to interpret complex electrochemical behavior like double layer capacitance, diffusion, or reaction kinetics just by looking at the shape and size of the curve.
Uh, this is the impedance values of the resistor, capacitor, and inductor, and the most physics electronics component. For the resistor, the impedance is equal to just only the resistance. However, for the capacitor and inductor, we need to use this kind of equation. This is the simple random circuit that represents the electrochemical system. In this simple circuit, we just have the solution resistance, and then connected to series with the parallel charge transfer resistance and the capacitance value. We have the counter electrode and the working electrode. By analyzing this simple circuit, we know the basic concepts of the electrochemical impedance spectroscopy. So what we would like to know is about the nature of the current flow from the low resistance of the low impedance value. So by analyzing this case, at first, actually impedance is just like the resistance. So if we connect the impedance in CD, we just need to do summation, and for the impedance in parallel, we just need to use this equation. So it means that for this case, we have this equation 13. In this equation 30, what we need to do is just substituting this capacitance value, impedance value, and the impedance value or resistance. And then we got equation 40. So by simplifying equation 14, we got equation 15. And by looking at the equation 15, we can know the nature of current flow. Of course, we have on the first bar, we just have RS, the current flow RS. However, depending on the high frequency and the low frequency, the current flow position changes. It depends on this equation system. When we look at the equation system, we found that the impedance set and the capacitance value, and then the omega is the frequency value, angular frequency is inversely proportional. It means that if we increase the omega value at that time, the impedance or capacitance is low. In this case, the current flow in the capacitance direction. So if we lower the frequency value at that time, the impedance value is high. At that time, the current flow in the upper RC circuit. So it means that in the higher frequency, the impedance is low, and that's why the current will flow through CDL. For the lower frequency, the current flows through RCT. So when we plot on the Nyquist plot, and we found that in the Nyquist plots, we don't show the frequency value, we just show this impedance of real components and the imaginary components. In the figure, the omega increase from right to left. It means that in this area is the highest frequency, and in this area is the lowest frequency. So for the equation 15, at first we need to increase the omega value. It means that if omega approach to infinity, at that time the denominator is infinity, and that's why this part approach to zero. So the total impedance must be equal to just only RS. That's why at the higher frequency, it just only show RS value. So if we decrease the omega value approach to zero, at that time, this term approach to zero, and just only one left, and it means that the total impedance is RS plus RCT. So as the lower frequency, the total impedance is RS plus RCT. So by looking at this Nyquist plot, we can measure the value of RS and RCT. If we know RS and RCT, we can use this equation 40 to measure the value of capacitance value.
Now I will explain why electrochemical impedance spectroscopy or EIS is useful. EIS is powerful because it allows us to investigate electrochemical process that happen on the different time scale. This is something on DC based method. And since EIS uses an AC signal, it provides unique advantages over the traditional DC technique, like the cyclic photometry. In many electrochemical systems, several processes occur at the same time, for example, double layer charging or diffusion. These processes happen simultaneously, but it occurs at a different speed. In regular DC experience, all these effects overlap in one command current. It makes it very difficult to separate and analyze them individually. EIS solves this problem by applying signal at a different frequency. Each frequency corresponds to the specific time scale, so we can separate the individual process clearly and understand them into more detail. Next, please. Next, I will explain how the EIS is measured on a battery. To perform EIS on battery, we use a 4-wire connection. Two of these wires are Next, I will explain how EIS is measured on a battery. To perform EIS on battery, we use the four-wire connection. Two of these are for current flow, and two of these are used to measure the cell voltage accurately. A frequency response analyzer or FRA work together with the electrochemical interference to apply the AC signal to the cell. The FIA sends through the signal into the battery through the current electrode level I, and the signal returns through the working electrode level I minus and I plus. At the same time, voltage is measured using a pair or reference point V plus and V minus. This allows us to measure the true voltage across the cell without error from the current carrying wire. And this diagram shows the full wiring configuration for the performing EIS on the battery.
Hi everyone. I figure you've learned a lot about EIS. So in this slide, we'll talk about its applications. We can use EIS in multiple occasions, such as in multifunctional sensors, which is applied in advanced resistive sensors, advanced capacitive sensors, advanced inductive sensors, and multifunctional sensors. Also in electrochemical sensors, it's used for electrodes, characterization, label-free measurements, highly sensitive sensors, and low limits of detection. Next slide, please. It is also commonly used in battery diagnosis and bioimpedance. For battery diagnosis, it's used for characterizations, states of health, states of charge, and inner cell temperature, and selections for second life. For bioimpedance, it is used for non-invasive, long-time tracking, diagnosis of organs, and cardiovascular diagnosis. Next one, please. EIS is also used in medical field. It's used in bioimpedance measurements. So there are lots of bioimpedance measurement methods, which are A, body composition estimation, B, impedance cardiography, C, transthoracic impedance pneumography, and for D and E, it's sulfate electrical impedance myography. And for F, it's electrical impedance tomography for lamp monitoring. That's all.